So it is a great pleasure to have today Abraham Neyman from the Hebrew University, who will tell us about an ongoing project.
Okay, thank you. Thank you for the invitation. And I will try to almost define any concept I'm using, but sometimes not at it's in its first appearance. Okay, because some already know what's the meaning of various concepts, so they get a picture from top, and therefore later details will come down. So it's an ongoing project with several, I think, interesting results. Otherwise, they could go open them, but others would think differently, and many open problems. Okay, so since there are many students here and faculty that look for intriguing open problems, there will be many of them mentioned. So, what are the main results? The first results that I'm going to quote here, I think I already gave a lecture here on it, but for the sake of the newcomers and for the sake of putting new results in perspective to the old results, it is worth mentioning it. The first results were on the big match, and all the work on the main results that I'm going to describe are joint work with two Danish scholars, one from Denmark, one from Liverpool, Christopher Hansen and Rasmus Ibsen Jensen. And I would say the 2021 are the old results, but they're going to be published now. I don't know why not yet published. I think there was a problem with the editorial of MOR. And the 2022 are new results, which we are not yet sure if they are going to be published in one paper, in two papers, because it depends how we close some of the gaps that we don't know how to answer. So the first two results relate to the big match. And the first one is a result that was presented here. So the first one says that player one in the big match, and I'll define the big match for everybody knows what's the big match here. Okay, in any case, I'll repeat it later, but so I'll do it quickly. So player one as an epsilon optimal, it looks here like epsilon one, but it's epsilon optimal strategy that is a finite memory strategy. And what is epsilon optimality and what is a finite memory strategy will be clear in the rest of the talk, later in the talk. Those who have been here in my old lecture do remember it. The new result about the
watch is included?
What?
Watch.
Yes,
watch.
a clock.
A clock.
Finite memory is with a clock, with random transitions, random actions, everything.
Okay.
And private, and it's private memory. Okay, so you could run for yourself some machine, some secret machine, update some memory. So the other one doesn't know how you summarize the statistics, you update your memory, and that's private. You know it. And indeed, you know, if you think of big data and things like that and cybersecurity, private memory is not always that secure, okay? Because somebody could penetrate and see maybe what is your memory by which you are playing. And therefore, a natural question is what happens what can you do with a public memory? So the other one goes into your machine and knows what's the memory, or you tell him how you compute the memory, even though it's a stochastic updating and so on, but he could see what is your memory state by which you continue. What is your summary of the history up to date? So the next, so first of all, on the first result, your question, we are allowing probabilistic and clock-dependent memory updating and actions. So the actions could be a function of the date, of the clock, of the number of the round, and the updating of the memory could be, and it's a private memory. And the question about public memory, and here is a new result, says that any public finite memory strategy of player one is worthless. You can do nothing with the public memory more than the worst payoff in the big match. And what is worthless, I haven't defined here, so it will become clear, and we will define explicitly in what sense it is worthless, what kind of measure of the values of a strategy, what does it mean that it is worthless? And there's still one open problem, because for another concept, we don't know that it is worthless. The other results relate to general finite stochastic games. So finite stochastic game, finitely many states, finitely many actions, two players, competitive players. And here, to state these results, we define a concept of an FN memory strategy. This is a strategy that uses no more than FN memory states in the first n stages of the game. So you may, a corporation, you gradually increase your computers, you could have more memory, but you want some bound on how fast the memory that you are utilizing is being used. And there will be here two results, okay? And basically the two results are one result, but it's easier to start with the first one, which is easier to understand exactly what it is, and we'll see that the first one follows from the second one that will be explained there. So in any finite competitive stochastic game, each player has a uniform. So those who are careful could see that before I talked about epsilon optimal, and here I speak about uniform epsilon optimal. Okay, and again, an open problem is, can we make it epsilon optimal in the strongest sense, like in the big match? A uniform epsilon optimal strategy that is a public O of log n memory strategy. A memory strategy, namely, it uses in the first n stages of the game no more than log n of states. But still, we allow that the clock-dependent mixed actions and clock-dependent transitions. And B2 is that there exists a uniform epsilon optimal stationary strategy, namely the mixed actions are just a function of your memory and the current state of the game. And with probability close to 1, uses no more than O of log n public memory states in the first n stages of the game. Now, why is B2 implying B1?
Thank you.
So, where is the marker here? So here you see, uses the number of memory states in the first n stages is no more than O of log n. And it has clock-independent mixed actions. Okay, the mixed actions are clock-independent, but still I allow a memory that is clock-dependent. And here we have a uniform that a clock-independent memory updating. So the memory updating is independent of the clock. Also, the mixed actions are independent of the clock, but we cannot guarantee that for sure we use no more than O of log n memory states in the first n stages, but only that with probability close to 1, we never cross this function at any stage of the game. Why this implies B1? Because if you play this and you are allowed to have clock-independent transitions, so once you are crossing the level, which happens with very small probability, play stupidly thereafter. Okay.
And it is stationary in the memory?
The memory updating and the mixed actions are just a function of your memory state and the state of it. Okay.
One more question about B1. So if we look at the optimal strategy of Mertens Neyman, there you have to record
O of n, not log n. We will later make a comparison of the previous optimal strategies, the properties. So in the Mertens-Neyman strategy, you need O of n memory states.
If you need to count the number of times you visited each state, each action. Is it enough? Currently, the strategy as it is presented in Mertens Neyman, it is that you have the virtual discount factor, and you add to it your payoff, your current payoff, and you subtract the min max value, and you round it up so that it's not below some bound.
Okay.
So if you wouldn't round it up so that it is not below that bound,
still you need O of log n. For instance, in the big match, the Blackwell-Ferguson strategy, we will discuss it. You need in the first 10 stages of the game n possible states, right? Because any difference between the number of lefts and the number of rights of player 2, you have to remember it.
we have to count the number of times you played left.
Yes.
And
this
to remember a number between 0 and n, it is sufficient to have log n.
No. I'm not looking on the number of bits that you need, but really the states of memory.
Okay.
Thank you for the question. Okay. So if in this case, if you would require to encode it with bits, then here you will need a log of n.
Okay.
So here we count really the number of states. So we will present these results, and we will also review many related past contributions and raise several open problems. So the big match that everybody knows is a stochastic game, consists of finitely many two-person zero-sum matrices. So here we have the three different strategies, and for each, when we play in each state one of a pair of actions, we are writing here what is the payoff to player 1, who is the maximizer, and player 2 is the adversary. And we have to explain what happens to the state, which game we are playing, as transitions from the actual game that we are and where we move. So if we are in these states, we stay there forever. These are the absorbing states. If we are at the top matrix and player 1 plays bottom, then depending on what player 2 played at this game, we are moving either to this absorbing state or to this absorbing state. Here, these are the two. And if we are playing any one of the top four entries, we'll come back to the same matrix. The largest amount of time that I spent on the preparation was to be able to make this drawing. So, but now I know how to do it, so it will be easy for future presentations. So the big match was introduced by Gillette 57, as you all know, and it was raised how player 1 can play if the game continues for a long number of rounds. How can he play? Can he play optimally? And it is an important example of a competitive stochastic game. Stochastic games were introduced by Shapley, and since this game by Gillette and the development, a lot of attention have been put on what we call undiscounted stochastic game or long-run stochastic game. There are various meanings for that. So we will talk. A pure strategy of player 2, what is it? Basically, player 2 has to play as long as player 1 played top before we absorb. Once we absorb, it's not important what he does. And therefore, it is a sequence of his actions, 0 for left or 1 for right. So remember that 0, the left one, was meaning that if we get absorbed at this state, we go to the payoff of 0. And if we get he plays absorbed on this action of player 2, we get to the absorbing payoff of 1, which means that if it was not absorbed on these actions, the payoff are reverse 0 and 1. Any questions so far? So a pure strategy of player 1, what is a strategy of player 1 in such a game? If you think of a pure one, it's just to decide what is the date by which you are playing the bottom strategy. Yes, and obviously this could be a stopping time, depending on what he learned in the course of the game from the actions of player 2. So the reward of player 1 at stage T is, as we say before, If we have not been yet absorbed, then it's 1 minus the action of player 2. And if we got absorbed, then it is the payoff of player 2 on the absorbing time. And if you just describe the big match to non-game theories, you could describe it just as described here, no game, nothing, no story whatsoever. So the reward to player, just for notation, the reward of player 1 at stage T is denoted RT, and the average of the rewards in the first 10 stages is the average of R1 up to Rn. What is player 1's objectives in the big match? So that depends. You should define what is the objective. So a play of the big match results in a stream of rewards. And note that you probably observed it, and that's one of the first things that we do when we do the big match, that player 2 has a strategy. If he mixes every day half and half, he guarantees that at every date, at every period, the expectation of the payoff at this date is 1/2. The payoff here in the big match were 1/2. But the objectives of player 1, there are various possible objectives. One of them is maximizing the end stage valuation UN. So you want to maximize the average of the payoff in the first end stage. The second one is maximizing the lambda discounted valuation of the game. And if these are the game, if n is given or lambda is given, you could do some small computation and prove that player 1 could guarantee a payoff of 1/2. But in this guaranteeing payoff of 1/2 in each one of these games, in the second example, it's sufficient to do some stationary strategy. And in the first one, a Markov strategy, so something that depends just on the data. But once you're looking on maximizing the lim int or the lim sup of the averages of the payoffs, there is no such simple strategy that will do it. And here starts the difficulty. And the important conceptual concept that I view, and many of the authors view the same thing, have the same opinion, but it doesn't mean that that's the only mathematical problem that is to maximize simultaneously all these payoffs for n, for all n sufficiently large. And if you do that, you simultaneously also maximize all these payoffs for lambda sufficiently small. So what is the Blackwell and Ferguson big match strategy? So they pick a sufficiently large number k. At stage T, they compute some statistics of the past play. The statistic is the number of previous stages by which player 1 played 0, player 2 played 0, the left column, minus the numbers by which he played the right. So you should realize that if he played 0, many times 0, you have to be very careful, because if you play the absorbing state, you will get into the payoff of 0. So if you see many zeros, you have to be careful. If you see many ones, you should be more latent. Okay, play 1, I don't care to play the absorbing state. And now I think you all probably read the newspapers or financial reports, and everybody will tell you past performance is not indicative of future performance. Wrong. Okay, in order to play here optimally in this sense, you have to take into account past performance. Okay, and that's what Blackwell and Ferguson did. Okay, because if you don't know exactly what is your payoff, it's either the 1,000th time repetition or the 10,000th repetition, nobody tells you. Eventually somebody will decide for you, and you have to optimize both of them. It's usually impossible without taking into account past performance. So they compute the statistics that I described in words, and the behavioral strategy, sigma of k, that depends on this particular constant k, says play at stage T the absorbing action with the probability that has this feature. The larger the number of zeros that player 2 played, you reduce your probability. And now it is some computation. I hope that everybody here made this computation to show that this is an epsilon optimal strategy. Before I state the optimality properties of the Blackwell-Ferguson strategy, we defined several optimality concepts. Also, as I said, some of the open problems relate to this type of optimality concepts. So PI is player one, player I, epsilon optimality in the big match. The strategy is lim sup epsilon optimal if for every strategy of player two, the expectation of the lim sup of the averages of the payoff is at least 0.5 minus epsilon. So you remember that for the end stage game or the lambda discounted game, player one could play a strategy that guarantees exactly, but here it means that he could guarantee those for the lim sup of these pairs. Let me mention here that Blackwell and Ferguson, when they wrote their paper, they were interested in this optimality. And they proved that player one has epsilon optimal strategy in this concept. But if you look on the proof, it proves also the other concepts, the epsilon optimality with respect to the other concept. And if we look on the order of the expectation of the lim sup is at least the lim sup of the expectation, which is at least the lim inf of the expectation, which is at least that, you realize that you could now come with various other optimality concept. If you will say that it is lim sup E optimal if it guarantees that the smaller amount here, no matter what is the strategy T, is at least 0.5, and so on, you go to the other concept. Lim inf expectation, if you guarantee that this payoff is at least, and the strongest epsilon optimality here with these four ranges is that it is, if you guarantee that this is at least 0.5. Obviously, if you guarantee that this is at least 0.5, you guarantee that all the rest are at least 0.5. And there is a concept of uniform epsilon optimality, which is not captured by any one of those, which says that there exists some sufficiently long number of games such that the same strategy sigma that we are speaking is optimal, is epsilon optimal in all the end stage games with duration at least n epsilon. So it guarantees that for every n epsilon. And if you remember, the first result was speaking about epsilon optimality, which is also the optimality that was proved in the Mertens Neyman paper, says epsilon optimally if it both uniform epsilon optimal and lim inf epsilon optimal. So the strongest among those four, which is lim inf epsilon, and in particular also uniform epsilon. Any questions so far? All concepts are clear? Okay. So properties of the Blackwell-Ferguson strategy. So we have to define what is the optimality. We say there are a few things. What is the memory size that they are using? What is the memory updating function? How it's updated, function of what? What is another property, if it's deterministic or realistic? The memory type, private or public, and the mixed action, on what does it depend, time or not. So the optimality of the Blackwell-Ferguson strategy is epsilon optimal, so in the strongest possible form. The memory size is O of n, exactly, compute exactly the function of n, it's of the order of n. We are not caring if it's twice n or 3n or 4n, the order of magnitude. The memory updating is deterministic. Yes, you remember the MT was just, you look what was the previous memory, you add one or you subtract one. The memory updating was clock independent. So it's a stronger property of it.
Why is clock independent?
Because you have your memory before, you don't care what is the time, how many rounds have, and you just see what was the new input on this round, and you update the memory, empty +1 or -1. Okay. And the memory type is public. It's a deterministic, but the moment that it is a deterministic memory updating, player 2 could follow up this memory and could compute it himself. You would understand. And the mixed action was clock independent. Okay. Question that I raised in 79, I think in a lecture first time was raised in a lecture in Stanford. And at the very end, I'll tell you some history about it, was, is there an O1 memory? O1 memory means that you never use more than some constant number of states, means that it is a finite memory strategy that is epsilon optimal. And here we allow everything, private, clock dependent, mixed, pure, and so on. And so this was the question that essentially motivated this line of research. I assigned it to many graduate students. No one made real progress on it. Some made some progress. And the answer is yes. And that's the paper, the 21 paper that I say that I already lectured. And if we look on the Hansen, Ibsen, Jensen, and my epsilon strategy, it is epsilon optimal, so the same type of optimality. It is O of 1, so that's the finite aspect. It is probabilistic memory updating. Okay. It is clock-dependent memory updating. It is private memory, and it is clock-dependent. If you think a little deeper about this concept, you see that if you stick with private memory, you could make the clock, you could make the probabilistic into deterministic one. And similarly, you could make the action, mixed action could do, I didn't write it here as a property, could be a pure action. Yes, because if you want to play half and half, in some memory, split into two different memories. The other one doesn't know which one. In one case, you play top, in one case, you play bottom. And so. Now, I say that the first new result is the worthless of a public strategy. So let us define again, what does it mean to be a worthless strategy for the big match? Okay, the big match, we know that the payoff was 0, 1, and the worst payoff was 0. So it is lim-inf worthless if for any epsilon, the expectation of the lim-inf is no more than epsilon. Similarly, as we did with the optimality, we have in an hierarchy. The expectation of the lim-inf is no more than the expectation of the lim-inf of the expectation is no more than the lim-sup of the expectation is no more than the expectation of the lim-sup. So you could have an hierarchy of stronger and stronger worthless properties. The next one is lim-inf of the expectation worthless, that this will be less than epsilon of this. If this is less than epsilon, this is less than epsilon, so it's a stronger concept. It is lim-sup E worthless if you guarantee the expectation of this is less than epsilon, and therefore obviously those ones are less than epsilon, and lim-sup worthless if you guarantee that one. Okay, let me throw up here, I mark this with the blue, because when I describe the result, I said that the result, I say that a finite public memory is worthless. The hierarchy that we could prove it is only this one. We don't know yet about that. We believe it is true also for that, but we don't know. Question? Okay, now about worthless strategies of the big match, there is a long history. So I'll describe any Markov strategy that's already in Blackburn and Ferguson, maybe even in Juliet, I don't know. And any finite memory and clock independent memory, that's an unpublished work of one of the graduate students, More Amitai, are lim-sup worthless. Namely, for every epsilon, there exists some strategy that will guarantee that even the expectation of the lim-sup of the averages of the payoff is no more than epsilon. In a sense, this strategy, if you formulate it correctly for a general finite stochastic game, you get the same result of worthless in this story. And then basically what brought me back into this topic, which I started thinking about it many years ago without success. And After my students failed to do it, I gave it up, and then I learned about the following result of Hansen, Ibsen, Jensen, and Cauchy from 2016 that proved that any deterministic finite memory is lim-int worthless. So the weakest worthless concept, but they are computer scientists. They were not aware about the different valuations, lim sup, expectation, non-expectation. So, and also the proofs are usually not in the standard that we as mathematicians think of as a proof. So they didn't know what is the exact worthless, but the ideas are there, and they prove that any deterministic finite memory is worthless. Namely, for every epsilon, for every such strategy of layer 1, there exists a strategy of layer 2 that guarantees that the expectation of the lim-inf of the averages is no more than epsilon. So if you remember, I made a comment that if you have a deterministic finite memory, any deterministic finite memory is in particular public memory. Because if it's
Deterministic means transition,
transition, memory updating. Memory update, no, or action
is
next, yes. The memory updating is deterministic.
in particular, no.
In particular, that because it's deterministic, the other player could compute it if he knows the strategy. Okay, and the new result is that any public finite memory is lim sup E worthless. So stronger worthless concept, and basically any finite memory. But we don't know, and this is the open problem, we don't know if it is true for the expectation of lim sup of the averages of the weights. So this is the minimum. So let's summarize the properties that we just talked to understand what are the open problems that are left. Water strategy in the big match. Markov strategy, its memory size is 0. You don't need it. Play clock dependent, but you don't need memory. Memory updating not applicable, not applicable. Memory type is public. Mixed action is clock dependent and worthless in the sense of the lim sup, the strongest possible thing. You could guarantee that it will not give you this payoff. The strategy of Amitai, the class of strategy that is studied is finite. The memory size, the memory updating is probabilistic. The memory updating is clock independent. And memory type is private. And mixed action clock independent. And the worthless is lim sup. This was his strategy. In the answer, Ibsen, Jensen, and Cauchy paper says that the finite memory with deterministic memory updating, with memory updating which could be close dependent, memory is public because of that, follows clock dependent, and this is worthless in the lim-inf. And our results guarantees that
Memory is clock independent in HK. There, yes, here.
Clock dependent. You could play. In Amitai, it's clock independent. Here, it's this stronger property. You could take the action dependent on the clock.
Give a hint on that.
On this proof,
Suppose
I could give later an hint to this proof, which is stronger. So, and so I hope I left some time to talk about the proof of this, and this will give some hint of this proof. Okay. So this result says that for every epsilon there exists a strategy. For every strategy that is finite memory, public finite memory, so the other player could compute the finite memory, is lim sup worthless, namely there exists a strategy of player 2 that guarantees that the lim sup of the expectation of this payoff is no more than epsilon. So if you are happy just with this result, I could stop here and go just to the proof, or I could also tell you some intriguing questions about general finite stochastic game. Maybe I'll give the open problem. So finite competitive stochastic game. So the optimality level is V minus epsilon. We cannot guarantee already in the big match exact uniform optimality. It's epsilon optimality. So we want to guarantee a V minus epsilon, where V is the limit of the values of the lambda discounted game. So you all know that it's the same of the lim of the end stage games and so on, and that there is a value. That's the optimality level that we are looking. And the worthless level that we are looking is the maximal undiscounted, and quotation mark, you will take whatever you want, each one of the version, a level that the stationary strategy can achieve. So you know that with a stationary strategy in any stochastic game, there is some payoff that the other player could bring you down. And this is the worthless level. So a stationary basically means zero memory. So you cannot gain anything worthless, when you say worthless, more than with a zero memory strategy. And let me give you an intriguing game, okay? So we say that the stochastic game consists of finitely many matrix games. So here are the 4 finitely many matrix games. And I changed a little the Bewley-Colbert game, because in every stochastic game in your teaching, I think you usually emphasize there is always a dilemma between maximizing the current payoff and where are you moving for the next state to have a good potential to good payoff from the next state. So I want to wipe out the issue of maximizing the present payoff. So in each one of these matrices, it's the same payoff. So you don't have a dilemma. You just worry about the potential of the next state. So these are the 4 games. And the bottom ones are the absorbing ones, like in the big match. Once we reach this game, we stay there and get to 0. If we play these 2 entry games in this matrix, bottom right, and this one bottom left, we move to these games. If we play the other corner of the game, we come back to the same game. And if we play any one of the other entries of the games, we are switching to these 2 games. So these games, these states are non-absorbing states. Yes, these states are absorbing states. So there is also another classification of stochastic game, which speaks about absorbing games, when there is just a single non-absorbing state. And in that case, the results of the big match carry over there as well. So this is the game. Oh. And the open problem that you could ask about any stochastic game, but does this stochastic game has a finite epsilon optimal strategy? In any concept that you want, give me the weakest concept of an epsilon optimality, that the lim sup of the averages of the payoff will be at least this value. The value of this game is 1/2 in each one of these states, and obviously here it's 0 and 1. So in a general stochastic game, the strategy of Mertens and myself speaks about epsilon optimality, this stronger concept. The memory size was the order of number of rounds that you have to remember. The memory updating was deterministic, so it makes the memory public. The other one could know what it is. The memory updating was clock independent. You just had some memory, and based on what happened in the current round, you are adjusting this. Have you been teaching them this strategy? So everybody knows about this strategy? Okay, good. And the memory type is public because it's deterministic. It is public. And the mixed action was clock independent. Just you tell me what is your memory and the states, I know how to play. And now I told you that there are 2 results. So let me give those 2 results by the strategy that in the new result that Ansen, Ibsen, Jensen, and myself have. And what are these properties? Optimality. We no longer know the same result that I'm going to quote, how to do it with epsilon optimal, but we could do it with uniform epsilon optimal in both cases. The memory size is O of log n. in the first one. In the second one, it's essentially O of log n. When I say it essentially, means that with probability arbitrarily close to zero, we never cross this function of O of log n of memory states that we utilize in the first stages of the game. The memory updating is probabilistic in both cases. The memory updating is clock dependent. And in this one, when we are willing to forego and having just essentially, then we could do the memory updating to be clock independent. The memory type is public. The mixed section is clock independent, clock independent. And the open problem is, in a general stochastic game, let's look for this weakest optimality concept that you could wish to prove. So I want to take the limb soup optimality, that you guarantee that expectation of the limb soup will be, of the averages will be at least some level. But can you do it with a finite memory, namely O of 1? And you're allowed to use memory updating, probabilistic, clock independent, private, and mixed section clock dependent. And another question that comes into mind, here I was asking, can you do it for finite memory? In our result, in our two results, either version, we use O of log n. So if the result is impossibility, this will be a stronger result, that you cannot do anything with even little O of log n of memory. I remember here we do limb soup, but if you want, change it to limb soup E of optimality and so on, because with O of log n, we know that you could do it for the optimality for the uniform optimality. So you guarantee that the limb soup of the expectation is at least. So I don't care which one of the results you prove, if they're positive or if you use the strongest or weakest concept for this type of result. Any questions? Thanks. So first of all, I'll give thanks. Thanks to you for listening. And then I'll have some time to answer at least the worthless aspect. So first of all, I want to thank Shapley. We all have to thank Shapley that introduced stochastic game, Gillette for introducing the big match, Blackwell and Ferguson for solving the big match, Kohlberg and Julian Kohlberg for his work on absorbing games, and Julian Kohlberg for the work of the asymptotic behavior of the lambda discounted game and the end-stage game. Mertens, who was a long time collaborator. We had several joint papers, but many more talks and discussions on many issues of. Also, he assigned this problem that I mentioned to one of his students, who solved it, but there was an error. So, in the proof, Jerry Green. How come Jerry Green here? Probably you don't know what is his relation to stochastic game. Indeed, no direct relation to stochastic game. But when I mentioned this problem in '79, yes, in a lecture in Stanford, and Jerry Green, who knows Jerry Green? You know, he knows everything, okay? Almost everything. He was also the provost in Harvard. But at the time, he was reading almost any paper in almost any journal. So he told me that if you remember the issue of a finite memory, it was clear there was already one result there, that if you look on stationary finite memory, namely clock independent updating, there you cannot play optimally. Any such strategy is worthless. And the way that I posed the problem, I said, here it's worthless, but what if it's clock dependent? You allow for clock dependent. Can you do it with finite memory? And he referred us to a paper, by Thomas Cover on hypothesis testing And he has two papers, one with with finite memory, and maybe the title is the same in both, but in one he proved that you cannot do hypothesis, and the other one he proves that you can. The one that you cannot was with stationary memory updating, statistics, so they don't speak about memory, they speak about the statistics, and the other one with clock-dependent memory. Okay? So I looked at the papers at this time. I referred my students or other students that wrote to these papers because it was a nice analogy. And indeed, in our proof, we looked again on it, and the solution is not there. You have to do much more work, but some of the ideas or one of the ideas is there. Okay, and then obviously to Hansen, Ibsen, Jensen, and Cauchy for their paper that re-initiated this topic, and for them for the joint work. Okay, so now how much time I have? 10 minutes. 10 minutes. Okay, so let me, I'll do two things. I'll try to give, you are all, or most of you are familiar with the Mertens-Neyman paper.
3 people took the class of practicing, so 4.
So I'll give you, on the second result, on general stochastic game, I would bluff you and give a proof. But obviously the details, the devil is in the details, how to do it. So let me give you an argument, and it's a pity I should have written it in the paper, even though I don't like to write in papers things that are not formal enough. But some, when I explained it to Bruno Gigliotto, he said, why you didn't quote it in the paper? I haven't seen this remark in the paper. So the issue is the following. In the Mertens, Neyman, and in the Blackwell strategy, what we do, we are looking on an additive function of the history. Okay? Like the Blackwell-Ferguson, how many left compared to how many right of player 2. You cannot do it with finite memory. It's limited. But with a finite memory, you could get multiplicative functions. Because transitions, if you have one probability of moving another probability, then you could multiply those two by your transitions. Okay? If I move to this place with probability, to this state with probability 1/2 and to the other one probability 1/3, making the two steps is probability 1/2 times, I don't remember what I said, 1/3 or so on. Okay, so the product of those two transitions. So kind of multiplicative functions you could do with transitions, with playing with transitions. Okay, so how do you transfer additive functions into multiplicative functions? With the exponential function. Okay, e to the power x for sufficiently small x is close to 1 plus x. So with the transitions, you could look on these sums and play them with the transitions. So basically, obviously, this is true only for sufficiently small x. So if you read carefully, you will see that in the transition of our papers, we look on e to the power lambda, some lambda sufficiently small, times these differences in payoffs, what we got compared to what we do. But obviously, after a long period of time, it starts diverging. So the lambda is ineffective. So the details, the details are such that you decide on a sufficiently long block, and you decide on sufficiently small lambda, such that these additions in this block, still we don't lose much by having this function compared to the additive function. And we play that. If we played absorbing or absorbed, if we don't play the absorbing according to this rule, we start a new block. And now the balance between how to play in the different blocks and how to choose the right lambda and so on. These are the details in the paper. But this is a kind of heuristic of the argument that is done there. What is the heuristic of the going from O of n to O of log of n? Okay, so if you are familiar, how do you reduce? So in our case, we move from in the Mercedes-Neyman from one statistics S to another statistics S prime, which usually was there in a number, but it was in the difference of a constant number from here. So each time that we switch, we count many switches. How we can reduce it? Instead of moving from S to S plus 1 or S minus 1, like in the big match, we move either to S plus a big number, a product of S times some number that is close to 1, or we divide it by this number. So we move to either of those things, but only probabilistically, so that in expectation, we keep track of what we wanted to count before. And this is the way that for the second results, we are saving on the time. And because of this issue with expectation, that's exactly where we fail to switch between the lim that we could guarantee the lim inf of the expectation, but we don't know if we could guarantee the lim inf of the averages of the pair. If we save this.
So instead of counting every step, do it in blocks?
No. Now for the general stochastic game, we can't.
No, in big match would be sufficient for me.
No, but you speak about the result of O of log n.
Yes.
O of log n. So if my memory was S, so in the big match, you either go to S plus 1 or S minus 1. Here I'll go from S to S times a number larger than 1, but sufficiently close to 1, gamma times S. Okay? Either to that or to S divided by gamma. So you take such a constant gamma. But so my memories will be S times gamma squared, and so on. But if I wanted to move according to the Blackwell-Ferguson strategy to S plus 1, I would move to S times gamma, but with the probability that the expectation of my change will be S plus 1, the conditional expectation, and similarly for the other. So the number of changes will be very small. And exactly what we are able to reduce it to O of log of n with this thing. Okay, let me maybe now go to the public memory. Ayran.
Hi. Sorry, I blocked the.
Welcome. Okay.
Okay. So what is a public memory? Okay. So we say that we are allowing it
זה
as
יד שנייה מפרופסור.
okay. So let's say that we have finite memory. So this is t equals 1, t equals 2. So the memory, since it is clock independent and we are allowing transitions that are time dependent, so basically the memory state is this finite set n cross the integers. So the memories are this set. But there is the rule that if I'm in this memory as a function of what happened in the game, I am moving to one of these states. Okay. So I'm going to define a best reply, not a best reply, a strategy if player 1 plays a public memory I'm going to define some strategy tau of player 2 that will guarantee that the lim sub of the expectation will be below epsilon, the big match. So I'm going to define a pure strategy of player 2 that is a function of the memory that we are reaching. So if we are reaching here, we will play pure. So if he plays pure, it means he plays either 0, which brings us to the absorbing at 0, or 1, which brings us, in case of absorbing, to 1. So such a strategy is basically defined by defining a subset of these memories by which you play 1. So we are playing a sequence of such strategies. Sigma 1, which is this, so tau 1, this tau 2, and so on. Such a sufficiently long strategy such that the number of times that you play 1, the number of cells that you play 1 is increasing. And there I'll define you what is tau. Okay, so let me start with tau 1. Okay, tau 1, player 1 plays, player 2 plays always 0. Okay, if player 1 plays always 0, then the memory of the public memory will fluctuate here and so on. But what is the probability of absorbing after time t goes to 0? So I could find some n1 such that the probability of getting absorbed here is very small. So I pick the smallness, okay, of this thing. And what I do is that I play in, now I look on the expectation sigma of tau 1 of r of RT. When I look on the sequence, so if I think already that I reach some tau I, yes, I look on this type of things. Okay, and then I would look, when is this more than delta? If it's always less than delta, okay, so the strategy tau 1 is fine, okay? If it is more than delta, there must be, you make some computations, you write this expectation as some function of where we visited at what probability. You guarantee that the probabilities that we are reaching one of these boxes is very small, and you will find here some place, in each one of those, you will find a place empty. This is empty such that, so if this expectation is larger than delta, you will find empty such that the probability that player player 1 played here the absorbing action is very small. So you will find here tau 2. So you look here on those many parts of MT, and you guarantee that the probability that you visited one of these boxes and you got absorbed is very small. So you look on pi of Tm. So pi of Tm is the probability that we have reached at stage T the memory M. So if this is a particular memory M, I look what is the probability that we reach this box. Okay, so you will get some, you will get many such places such that the sum of these probabilities is very small, yes, and the probability that player 1 plays, so summation of sigma of Tm of the absorbing action. These are all the T that is larger than some sorry, T at least some N, let's say. I'll guarantee that this is, by the properties of the payoff, that this is very small. If this is very small, sorry, sigma Tm CF2. Okay, let me do this. Using U, so expectation of RIT equals, what is the expectation of RIT? It is the summation of PIT, PIM. See what I PITM, so all TM that are not tau I, plus the probability I of getting absorbed 1 before time t. So if you look, what is the expected payoff at stage t? Maybe you have absorbed before at stage 0, at the absorbing payoff 0, the payoff will be 0. If you absorb before at state 1, the payoff will be 1. What is this probability that you absorb before this state? This one. Okay. And this is the probability, if you look just on the sum of all the m, such that Tm is not in tau I. So you mark here those that you played 0. Yes. You remember, if you are not absorbed, when you play 0, you get player 1 gets payoff of 1. Okay. So you look on these things, on those m, such that this is not in mi. So it means that you play 0 there. And this is the sum. And this is, you could break it into two sums, summation, all m, such Tm, not tau I, Pi Tm, sorry, not in, times the indicator of all the indicator of all the Pi Tm, at least delta over 3m. M is the number of memory states that you have here, plus summation of all Tm is not tau I, such that Pi Tm times indicator of Pi less than delta over 3m. Plus this term. Okay?
What is the delta over 3m?
So the indicator. So here it's times 1. So I break 1 into two parts.
Okay.
Some of them are m, where the probability of reaching here is above some level, and some that are below some level. Plus this one. This I could make as small as I want. Okay? Sorry, one of the conditions of the strategies here is that this will be sufficiently small. Let's say that it is less than delta over 3. Okay, and I'll keep commenting that this is the case. That the probability of that is less than delta over 3. Okay, so this will be strictly less than this plus delta over 3. What is this sum? How many summons do we have here? At most m. Each one of those will be less than delta over 3m. So this term is also less than delta over 3. Okay, so if this is at least delta, it implies that there is here something, that this is non-zero. So it means there exists some m that is not in tau I for each one of those, such that there is some m, such that pi of tm is at least delta over 3m. Okay, so basically the first thing will be to decide on this ni for the strategy I, such that going afterwards, this would still, the probability of absorbing there is going to be sufficiently small because all of it was less than delta over 3. I could find a place for which it will still, the difference will still make it less than delta over 3. And therefore, eventually you get here that for every, so the expectation of RIT, at least delta, implies that there exists, that for every t sufficiently large, then ni, and without loss of generality, then ni, we could make them increasing. There exists mt such that pi of tm is at least delta. Okay, so you guarantee that if this was less than at least delta, you could plug those things. And because of this issue that the probability of the one star is less than delta, and on all these places where this is more than delta over m, you could guarantee that the probabilities of this, that this will be very small, sufficiently small as well. So on all these places, yes, you are switching tau I plus 1 to be playing 1, to increase there from 0 to 1. Yes. So here you increase. Now, how many increases can you have for a particular t? How many times can you increase? For any t, when you look on the sequence of tau I, part of those are 0, part of those are 1. And if the expectation was more than delta, there was an additional 1. So how many times can we increase? At most m times. Okay. So the fact that we can increase at most m times, if you will take a sufficiently large number of these sequences, yes, you will guarantee that the average of them, okay, so if you look on tau to be tau 1 plus tau k divided by k, so you play strategy sigma k with probability tau k, and you compute what should be this larger. I think 3m would be enough with this computation. You will guarantee that for after nk, after the nk, it's impossible that you will have more than m places with this condition. Okay, I think I'm losing you and time is running. So the best is to look in the paper, and this will basically prove that the lim sup of the expectation. So here this is bringing the expectation. Now, if you look on the Hansen, Ibsen, Jensen, and Cauchy paper, which was your question, is you do a similar thing with these strategies, but basically sufficient to take tau I sufficiently large. You don't have to take the averages. Okay? There is one of those that you will guarantee the lim sup of that after you make many steps, because the number of times that you are adding here, the one without affecting the probability of absorbing into the from state is bounded. Okay, so you'll have enough sequences by which this will be. Sorry, I think I lost you on this computation. The paper is ready without the introduction, so I could send it to Elon if those who want to look on the details of the computation.
Yeah.
Okay.
Okay, so thank you. More questions? Okay. So thanks again.
I hope that next time somebody here will solve one of these problems.
Yes, I agree. Yeah. Okay. תודה רבה.
Okay, תודה.
Cheers.